Now, we have these two terms that we're trying to balance between each other, and there's going to be a parameter, just like in regression, that helps us explore how much we put emphasis on fitting the data versus how much emphasis we put on making the magnitude of the coefficient small. And this parameter we call lambda, or the tuning parameter, or the magic parameter, or the magic constant. And so if you think about it, there's three regimes here for us to explore. When lambda is equal to 0, let's see what happens. So when lambda equals to 0, this problem reduces to just optimizing, to maximizing over W of the likelihood only. So only the likelihood term, which means that we get to the standard maximum likelihood solution. Unpenalized MLE solution. So that's probably not a good idea to set it to 0, because I have this really bad overfitting problems and not preventing any overfitting. Now, if I set lambda to be too large, for example, if I set it to be infinity, what happens? Well, the optimization becomes the maximum over W, or of L of W, minus infinity times the norm of the parameters, which means the L of W gets drowned out. All I care about is that infinity term, and so that pushes me to only care about penalizing the parameters, about penalizing the coefficients, as to say, not the parameters, so penalizing W, or penalizing the large coefficients, which will lead to just setting all of the W's equal to 0. So everything will be 0. Also not a good idea, because I'm not fitting the data at all. I set all the parameters to 0. It's not doing anything good, ignoring the data. So the area that we care about is somewhere in between. So a lambda between 0 and infinity, which balances the data fit against magnitude of parameter of the coefficients. Very good. So we're going to try to find a lambda that's between 0 and infinity that fits our data well. And this process, where we're trying to find a lambda and we're trying to fit the data with this L2 penalty, it's called L2 regularized logistic regression. In the regression case, we call this ridge regression. Here it doesn't have a fancy name, it's just L2 regularized logistic regression. Now you might ask at this point, how do I pick lambda? Well, if you took the regression course, you should know the answer already. Don't use your training data, because as lambda goes to 0, you're going to fit the training data better. You're not going to be able to pick lambda that way. Never ever use your test data, ever. So you either use a validation set if you have lots of data, or use cross-validation for smaller data sets. So in the regression course, we cover this picking the parameter lambda for the regression setting, and it's the same kind of idea here. Use a validation set or use cross-validation, always. Lambda can be viewed as a parameter that helps us go between a high variance model and a high bias model, and try to find a way to balance the bias and variance in terms of the bias variance trade-off. So when lambda is very large, we have W is going to 0, and so we have large bias. I'm ignoring the data, I'm not fitting the data very well, but we have low variance. No matter where your data set is, you get the same kind of parameters. In the extreme, when lambda is extremely large, you get 0 no matter what data set you have. If lambda is very small, you get a very good fit to the training data. So you have low bias, but you can have a very high variance. If the data changes a little bit, you get a completely different decision boundary. And so in essence, lambda controls the bias variance trade-off for this regularization setting in logistic regression or in classification, just like it did in regular regression.